Hello guys, Mr. G here with the other video on the electrostatic test. We're going to be doing questions 3 and 4 and then we're going to be ending with a video. Yesterday I posted the worksheet so you can answer all the questions and see if you can get the correct answers. But without any more, we're going to start. But before we start, please remember to subscribe for the channel so you can get the notifications as well as the answers and all the videos, the worksheets I'll post, and more things will be posted. But anyway, we're going to start with question 3. Question 3 is a very interesting question, which it looks simple but is a little bit confusing, and there's something that you must learn there. The question 3 says two identical neutral spheres, and this is a very important word here, the part neutral spheres. So there is no charge. These spheres here, none of them has charge because they are neutral. So let's write here neutral. M and N are placed on isolated stands. They are brought into contact and a charged rod is brought near the spheres. Now these two are neutral, so nothing happens there. But this charge, this one is charged, which is either positive or negative. We're going to see that one right now. Now they say when the spheres are separated, it's found that 5 times 10 to the 6 electrons were transferred from M to N. It was found that later on when they were separated, the electrons transfer from M to N. So some electrons, many electrons move from here to there even though they are neutral. Now why is this one like that? Because this charge rod was then negatively charged, and when you approach the rod to the charged spheres which were neutral, the electrons were moving. Most of the electrons moved to this side here, and then most of the protons or positive charge moved to this side here. So that is why some electrons were transferred from M to N. I hope you understand this one. It's quite tricky. It's not just like that. So that is the main thing here. Now question 3.1, calculate the charge on sphere N after separation. Now we are going to use charge quantization. We did a question like this one previously, so it's not a big issue, but let me show you what formula you have to use here. Here is the formula for charge quantization, guys. It will be given like this in the exam, so please make sure you look for it. Don't memorize formula. You can, but you don't have to, because you will have all the information. And remember, here in this table also you get the charge of the electron, which is important obviously in this topic. So transferring that formula here, number of electrons is equal to the charge divided by charge of one electron. I'm going to write QE, but in the formula, in the data is just E, and that is also correct. Remember, this charge is not necessarily the charge of the electron, it is the elementary charge, and therefore it could be the charge of the electron or the charge of the proton. So if you substitute here, guys, now I substitute negative because what it was transferred was electrons. You can see it here in the information. So that one have an excess of electrons right now, and therefore when you do this calculation, you will get that the answer is minus 8 times 10 to the minus 13 coulomb. This is a very interesting question. Very interesting. It's a good question. I like it. It's kind of different. So this is the answer for question 3.1. Now question 3.2, write down the net charge on sphere M. Now note, electrons were transferred from M to N. Now they were touching each other. This is conservation of charge. So the total charge must stay constant. Initially the total charge was 0 and the electrons were transferred. So the final charge, the total final charge of the system must be also 0. So the charge in object M is going to be equal to 8. It's going to be exactly the same but positive. 10 to the negative 13 coulombs. And that is the answer for this question 3.2. It is kind of tricky, guys. So it is a little bit tricky. I hope you understand what I explained here when the charge rod is approached. But if you don't, please don't hesitate and you can ask questions. I will definitely answer as soon as I receive the question. Now let's go to the next one. The charge via M and N are now arranged along a straight line in space such that the distance between the centers is 15 centimeters. Remember, we have to convert to meters. A point P lies 10 centimeters to the right of N. Now remember, the points P are always positive. This point here is going to be positive. Points are always positive, as shown in the diagram below. So here the distance, this one is 15 is 0.15 meters, and this one is 0.1 meters. That is important because you need to convert to meters. Define electric field at a point. And I want you to do the following. We're going to go to the formulas. And here, guys, this formula, this one here, is the definition for electric field at a point. Now, how do we read this formula there? Well, we read force per unit charge, but this charge must be a positive charge. So we said that force per unit positive charge. Guys, this one is quite simple. It is in the formulas. So if you are studying right now, if you're watching the video and perhaps you're answering a question, go to the formulas in the exam and then write next to this formula electric field at a point. This one is the electric field at a point. So make sure you have this formula, and you do that. If you have with you the examination guideline, is even better. You do it there in the examination guideline, so you can always go there when you're studying and looking for this one, guys. This one is question 3.3. So we carry on. Question 3.4. Calculate the net electric field at point P due to M and N. So let's see what is happening at point P. Now at point P, here is going to be point P. This one is point P, and remember, point P is positive point. Okay, now both charges are having an effect on point P. So the electric field P is different for M and is different for N. So let's start with M, and we're going back here. M is a positive charge. M is positive charge and N was negative charge. This is very important. You need to know what is the charge of each of them. So M, the electric field due to M, or the electric field at point P due to M, is going to be away because it is positive, and positive repel each other. So this one here will have an electric field which is going to be pointing to the right. This is electric field at point P due to charge M, guys. This is the thing here. And then M is going to be pulling towards itself because it is a negative. So the electric field at point P due to N is going to be to the left, and it's going to be bigger in length. I'm not doing it accurate, but it's going to be bigger in length because the distance has an influence here. So this is electric field N. Now they ask us to calculate at this point P the electric field net. And remember, we're talking with vector quantities, guys. So net electric field, which I'm going to write it on this side here, the net electric field will be the vector addition of electric field N plus the electric field M. These are vectors, therefore we have to select a positive direction, and it does not really matter which direction you select as positive. the answer will be the same. So because En is bigger than the Em in magnitude, let's say this direction is going to be the positive direction for us to have positive answer at the end, but it does not really matter. Guys, be careful with that one. Now, what we are going to do, we are not going to substitute the formulas here. We are going to calculate individually. So the electric field at point N, how do we calculate this one? We are going to the formulas. This one is an electric field which is not uniform, and we are going to use that formula there. This formula is for the electric field when the electric field is not uniform. Not uniform means that it changes due to the distance. And that is the case here. So the formula is K multiplied by Qn divided by the distance square. And all we have to do is to substitute. Now, important, in this substitution, all the values are going to be positive. So you don't substitute the negative of the charge if it's any negative charge. That is an important detail because you attempt, or people attempt, to get confused and substitute the negative or positive here. Now, important, N is 10 centimeters. That's not an issue. 0.1 square. So the answer I get here 0.72 Newton per coulomb. That is the unit, and that is the first answer. Now we are going to do the same for electric field M. Now, before we substitute, because I'm going to fast forward for the substitution, you need to know that the distance is from here to the point. So that is the distance, and that will be 0.15 plus 0.1 is 0.25 meters. That is an important detail here. Be careful you don't confuse, but I'm going to fast forward for this one. And the answer here is 0.1152 Newton per coulomb. You can convert it in scientific notation if you wish. It's not a big problem. But now let's go and calculate the net electric field. Remember, electric field is a vector, so at the end it would have direction. En is going to be positive. It's positive because of the direction, so it's 0.72 plus, but Em is negative because it's in the opposite direction, minus 0.1152. You don't have to write the bracket plus minus. It's can substitute the minus there, and then the answer is going to be 0.60. Rounded off to 2 decimal places, okay, but it's going to 48, so it's up to you. You can round off to 2 decimal places, Newton per coulomb. And then, guys, this is the answer, but direction because it's a vector, so I'm going to write left just to finish this question there. So guys, this is equation 3. My humble request is to try to do the answer. I think it's quite tricky. This part here is very interesting because it's polarization and induction, charge by induction. So it is a little bit confusing, but please, you can write comments if you did understand or if you did not understand, and I will re-explain. Let's go to question 4, and it's the last question of this test. And this question says 3 point charges Q1, Q2, and Q3 are placed in a vacuum as shown in the diagram below. Charge Q1 has a charge of positive 6 times 10 to the minus 6 coulomb. Q1 is positive, so let's do here trying to change the color. It's a positive charge there. Q2 has a charge of positive. Q2 is also positive. 3 times 10 to the minus 6, and charge Q3 has a positive. So all of them are positive charges of 6 times 10 to the minus 6 coulomb. Draw a free body diagram to show the forces acting on point charge Q2 and find the resultant force that act on Q2 graphically. Ignore gravitational force. Important. So in other words, the only force that they want us is the electrostatic force. So let's do a force diagram first there on the diagram so you understand, and then we're going to do it separated. So the force that Q1 exerts on Q2 will be to the right. This force here, because they are two positive, so this is force 1 on 2, is pushing it away there because they are positive, so they repel each other. And the same happened with a charge 3. Charge 3 is repelling charge 2 in this direction, so this one is force 3 on 2, guys. And then that is it. Now they want the resultant. Ignore the gravitational, say find the resultant force that act on Q2 graphically. Now they don't want you to calculate it, they just want to show the resultant. And the resultant here, this is vectors done in grade 11. If you use the parallelogram system here, this is the resultant force. This is the method called in South Africa tail to tail. And this one is F net at point Q2. Now we're taking all this one and we isolate it from there to have the correct answer in actual fact. So I'm going to do it right here on the right in a small space there. And here on the left, I'm going to do it on the left, is question 4.1, which is just the free body diagram, exactly the same as here, but clean and properly done. Question 4.2, which is the final question of this wonderful test, say calculate the magnitude of the resultant force that act on point charge Q1. Now, because this is a 2D diagram is a little bit different from this one here. Here we have to use Pythagoras. We're calculating, guys, this net force there. This is what you calculate they ask you to calculate the magnitude only. So for the magnitude, this is a triangle, right angle, as you can see there. Let me use the same color. This one here is the F3 on 2. You can see it's a triangle, right angle, and you're looking in actual fact for the hypotenuse. So all you have to do here to calculate the magnitude they want to calculate is to use Pythagoras. So for the net force, calculate the magnitude of the resultant force, you have to use Pythagoras, which is square root of F1 on 2 square plus F3 on 2 square. I recommend you to do it. I always recommend, guys, to do the question separated step by step. This formula we used it in the first video, so I'm not going to go to the formulas to show where it is, but you can go there. So I like to come here and say F1 on 2, and I calculate this one, K, Q1, Q2, divided by distance 1, 2 square. And I do the same with 3 on 2. I'm going to substitute and fast forward all this calculation because it is not necessarily to do it right now on video. And guys, this is the end of the question and also the end of the test. But thank you for watching. This is quite simple. It's a very good test to practice. Remember, in June, guys, you will have a provincial test. Mostly all the provinces will try to set up provincial tests for all the grades. So this one is a good test, not only for the grade 11 but for the grade 12. I believe it will be more important for the grade 12 because they done it last year and it could be in the exam in June. But thank you for watching. Subscribe for the channel, thumb up if you like the video. If you think it helped, you can write messages. I'll try to answer as soon as I can. I'll see you next time. Mr. G here.